Okay, in this video we're going to look at something called Kw, which is the ionic product constant of water. Okay, so there's something called proteolysis, which is when a proton is transferred between two identical molecules, one acting as a Bl, means Bronsted-Lowry acid, and one as a Bl or Bronsted-Lowry base. So here is a diagram of showing you what is happening. So we have two molecules of H2O, and one of them is donating a proton to the other, leaving us with H3O plus, because there's the extra, or there, whichever one is the extra proton. And of course, one of these molecules has lost a proton to give you OH negative. Okay, so we can write this as an equation like this. So two molecules of water, and it's a reversible reaction, so we have an equilibrium, and we have H3O plus OH negative. Okay, now another way you might see this written is like this: just one molecule of H2O on the left side, and then simply a H plus OH negative. Now both of these mean the same thing, so you can choose this equation or this equation, whichever one. I think maybe the second one is easier. Okay, now if we were to write a Kc, which would be the products on top, now I'm going to choose the second equation to write this. So it's products on the top, and then we have the reactant on the bottom. Okay, so we can write a Kc, an equilibrium expression for this reaction. Now, because so little of this, the water, so little of this ionizes, okay, we can combine these two, the Kc and the H2O, to give us something called Kw. Okay, so Kw is written like this. Okay, so you have to know how to write the expression for Kw, and it's simply the concentration of the H plus times the concentration of the OH negative. Of course, another way it could be written is with the H3O plus, if you prefer that way, and then the OH negative. Okay? Okay. So let's go on to an example using Kw. So we have at 298 K, the ionic product constant of pure water is 1.00 times 10 to the negative 14. This is something you need to know. So at 298 K, Kw equals 1.00 times 10 to the negative 14. Okay? And what we can do from this is we can calculate the pH of pure water at 298 K. So let's do that now, shall we? So we write the equation, which is Kw equals H plus times OH negative. Now, for pure water, the concentrations of the H plus and OH negative are equal. Okay, so basically, to find the concentration of the H plus, you would take the square root of 1.00 times 10 to the negative 14. Okay, and then if you do the math on that, you'll end up with 1.00 times 10 to the negative 7. Now you may remember, or you should remember, that pH equals negative log of the hydrogen ion concentration, which is this equation here. So if you input the negative log of 1.00 times 10 to the negative 7, you get pH of 7 at 298 Kelvin. Okay, now you'll see later why it's important to specify the temperature when we quote a pH value. Okay, so we'll have a look at why that's important in the next example. Okay, so because Kw is an equilibrium constant, it's temperature dependent. You may remember that the only thing that changes the value of Kc is a change in temperature. Okay? Second point, the dissociation of water is endothermic. It takes energy to break that water molecule up into the H plus and the OH negative. Third point, an increase in temperature shifts the equilibrium to the right. So why don't we have a look. Just bear with me a second. Just get rid of that. Okay, so here's the equation for the dissociation of water. Okay, so you got the H plus and the OH negative. Okay, so the forward reaction is endothermic. Okay, so basically if you increase the temperature, which way is the equilibrium going to shift? Well, if you increase the temperature, the equilibrium will shift to the right. Okay, I'm sure that's what you were thinking. So basically, if the equilibrium shifts to the right, then the concentration of H plus and the concentration of OH negative will increase. Okay, and if you may remember that Kw is equal to this. Okay, so if the concentration of these two increase, well then the value of Kw will increase too. Okay, and one more thing, if we're increasing the concentration of the H plus, what's going to happen to the pH? Now you may also remember that if you increase the concentration of H plus, the pH will decrease. Okay, so basically we can say if temperature increases, then pH will decrease. Okay, and we'll have a look at this in the next example. Okay, so here's our example. The Kw of pure water at 323 K is 5.5 times 10 to negative 14. What is the pH? So this question is asking you, what is the pH of pure water at 323 Kelvin? So we learn, maybe in junior high school, that pure water is neutral and therefore it has a pH 7. Well, that's not quite true, as we're going to have a look now. Okay, so basically you can write your expression for Kw, okay, which is H plus multiplied by the concentration of OH negative. Okay, now like I said before, in pure water the concentrations are equal. Okay, so we can take the square root of the Kw, so concentration equals the square root of 5.5 times 10 to the negative 14. And by the way, if I wanted to know the concentration of this one, I would just put OH negative equals the square root, because these are the same. Okay, so basically if you do the math on that one, you end up with 2.35 times 10 to the negative 7. And then you can calculate the pH, which is negative log of the hydrogen ion concentration. Okay, so if you do the math, input that value into there, you end up with a pH of 6.63. Well, you can see now that the pH of pure water, I mean the pH of a neutral solution, which these two are equal, is not always 7, is it? Because Kw is temperature dependent. Okay, so basically you can see that we've increased the temperature and the pH has decreased. Okay, so you can say that pure water is pH 7 at 298 K, but at 323 K the pH is 6.63. Okay.